Yeah. I don't have them.
All right, so we're just going to start by warming up on our unit conversions that we left off on. So the last three on these page, we have meters to decimeters, decimeters to millimeters, and centimeters to millimeters. So go ahead, try to warm up on those, and then we'll, of course, go over them. Oh, and I do have periodic tables. Let's try the first one. Does someone want to put it on the board for us, 77 meters to decimeters? Oh, just, yeah, like write it out for us. Yeah, if you want to do that. There should be markers over there, and the far board is perfect. And then just kind of walk us through, if you can, to your thought process.
I just moved for deci to smaller. So I just move 0 over 2 places.
So move it over 2 places. 2 places, or?
Oh, I'm sorry, just 1.
Yeah, 1 place. And so I'll kind of write it out more formally. So 77 meters. And then I just used our relationship that we have 10 decimeters and 1 meter. And then you get the same answer as Bray over there of 770 decimeters. Good. Questions on that one? Good. Ask questions now. So this one could have been a tricky one. So maybe you have to come up with your own conversion factor, or you could do a 2-step conversion. What do we get? Anybody want to put it on the board for us? Max, did you do this one?
I'm sorry.
Still working. You want to try it? Okay, go for it. Brave volunteer. And then, yeah, the far board is fine. I can just read that one easier.
From what you told us, you said 1 meter is 10 decimeters. So I've got decimeters already. Meter. And we needed to convert into millimeters. And 1 meter is equivalent to 1,000 millimeters. So doing the method that you taught us, I said 37 decimeters over 1, which we take from this conversion of 10 decimeters into 1 meter, times 1 meter, that is equivalent to 1,000 millimeters. And then the units will cancel one another, and then we left with meters. And the final answer that I got is
Oh, I think you lost a 0.
wait,
You have it set up right. Yeah. So it's 3 zeros minus 1 0, so you need to add 2 zeros.
oh yeah.
But yeah,
So
the
it's
work,
3,700.
perfect.
Yeah.
Yeah, I was going to say the work, the setup looks excellent. And so, right, we could kind of call this a 2-step conversion formally, going from decimeters to meters and back to millimeters. And that was good, right, since we have those. If you, again, wanted to, right, you could think about how deci is 10 to the negative 1, millimeters is 10 to the negative 3. So you have that factor of 100 difference there again, which is what we ended up with our dimensional analysis. So again, if you kind of like that, you see that, go for it. Excellent. Questions on that one? And so let's do our last one. So again, this is another one where maybe we want to come up with our own conversion factor, especially given what we know about millimeters and centimeters. So do we know how many millimeters are in a centimeter?
1 centimeter is equivalent to 10 millimeters.
Excellent. So this might be easier just to come up with. Otherwise, right, you might have to go centimeters to meters, back to millimeters. Either way. And so then we can just do this one together. 2 centimeters, 2 millimeters. And so then we should get 0.02 millimeters. Or that's another one. Again, you could recognize centimeters 10 to the -2, millimeters -3. So there's our factor of 10 difference again between them. All right, that's pretty good. So let's continue on. And so now we want to talk about significant figures, which was pretty relevant to today's lab. And so again, we want to think about what just happened in lab today. Because kind of the whole point of these significant figures is that it needs to be reflective of our glassware. So that's why I was saying, like, okay, if we have, this graduated cylinder, we can only report out to the 10th place, and you want to write that accurately. Or if we were using, the more accurate graduated cylinder, report it out to the 100th place, because you want to, again, reflect the precision of the glassware. So that's where the sig figs comes from. And so same thing, that's why with the scale, you want to record every digit on the scale, even if it ends in a 0, right? Because again, that's saying how accurate. So we can measure, to the thousandth place accurately, and we know that that's a 0. And so as we do our calculations, though, so we'll have a few little caveats that we'll look at. For example, conversion factors are treated as exact values. So obviously, that just means like if we're doing this 1 inch to 2.54 centimeters, we don't want to kill, right, our sig figs here. So these don't count. Rather, it just depends on whatever we're converting from. So these are not included. They have infinite number of sig figs. And so then let's go through these kind of rules formally, because we also have to write our answer accurately and reflect, again, the sig figs. And so the first statement is pretty straightforward. So all non-zero values are significant. Well, that makes sense. So here, right, we have 536, 3 digits, 3 sig figs. And then the next one is also pretty straightforward. I kind of call this our captive 0, meaning we have a 0 that's trapped between some non-zero digits, and so of course it has to be significant as well. So 6,703 has 4 sig figs. And so now we get to these next two, and basically these have to deal with magnitude, and we'll look at it. And so the first one is saying that we have these leading zeros. And so, okay, let's just read it, and then we'll dissect what it's trying to tell us. So it says, placeholder zeros to the left of a non-zero digit are not significant. And so let's think about what this is showing, right? So this is showing how small. And so kind of the other way to think about it is if we can just kind of rewrite it, and it doesn't matter, right? So we can rewrite it in scientific notation, so 4.3 times 10 to the negative 3. And so now we're really showing that, okay, all that was doing was telling us how small. And so once we rewrite it in scientific notation, we can clearly see, right, 2 sig figs. Does that make sense? And then the next one is the opposite, right? So now it's trailing zeros. So zeros to the right after a non-zero digit are not significant. So again, now let's look at 7,000 or either this other one. So 32,040. And so again, 7,000, this is just showing how big. And so we could rewrite it, as 7 times 10 to the third. That's also, right, again, we got rid of the zeros. And then for this one, same thing. We could either rewrite it in scientific notation. And then question in the chat. So scientific notation properly is just 1 digit and then, right, the next subsequent digits. But it's always just like 1 digit and then obviously times 10 to whatever power. So that's just a form of scientific notation, if that makes sense. All right, so then we have how small, how big, and then our last rule is now showing us accuracy. And again, we have to think about what this is saying. So now it's telling us, okay, zeros to the right after a decimal point are significant. And so now we're looking at 50.0. And so this is, again, right, it's reflective off of this last zero here. This was unnecessary, right? We really just needed the 50, but of course we would only have 1 sig fig. And so adding this 0 here is showing us, well, whatever measurement this is, right? It's not really clear what this is, if it's a mass or a length, but basically we know it to the 10th place, and we know that it is a 0. And so same thing, you could rewrite this, right, in scientific notation to reflect accuracy, but let's do this one for instance. So we have 0.0600. Again, these are showing accuracy since they're unnecessary, right? But this one is showing how big, or how small, I guess. And so we could rewrite it as 6.00 times 10 to the negative 2. And this more clearly shows, right, that we have 3 sig figs. We measured this accuracy, and then this 10 to the minus 2 then shows how small in this case. So does that kind of make sense on those basic rules so far? And then we'll do some practice. And so again, y'all just had lab this morning, but if you're not in the live class, right, you still want to pay attention to the video because again, right, that's part of the lab is measuring accurately. And so again, you just finish doing this. We'll just kind of go through it together. So we have water with our meniscus here, and we can measure it accurately, right, to 4.5. And then our last digit is uncertain, and we can estimate it, right? So 4.56 or 5.5, whatever, right? And of course, you can have different values for that last one. So kind of same thing, you have that in your pre-lab question. All right, let's try just our practice. So take a minute or two, just kind of think about this in your head, write it down, and then we'll kind of go over with fingers. You can show me how many fingers, how many sig figs. All right, let's see what we're thinking. So just show me fingers. How many sig figs for number 1 here? So I see 2, 2. Some uncertain votes. So 2, excellent, right? So we just have 2 sig figs. These zeros are showing how big, and of course we could think about rewriting it in scientific notation. That helps us. All right, what about number 2? How many sig figs there? So 3, excellent. So captive 0. What about number 3? How many for that one? So I see mixed answers, some 3s. So it should be 3, right? So don't leave off that last 0. So that one is showing accuracy. All these are showing how small, so they don't count. But yeah, just don't forget about that 0 at the end. And this would be another one that would be good to rewrite as 2.10, and then 1, 2, 3, 4, 5, 6. Just making sure I counted that right. Sometimes get a little squirrely looking at those zeros. And so again, just kind of rewriting it in scientific notation clearly shows that we have the 3 sig figs. So what about 4? How many sig figs? So 2, excellent, so 2. So again, how big? We can think about rewriting it to make it clear. What about 5? This one's a little weird. How many sig figs? So yeah, 2. That was good. So this one is weird, and we should talk about it because so we can see, right, we put this decimal point there. And so by putting the decimal point there, that is showing that, yes, that 0 is significant. Kind of the problem with that is, right, if you were to read that in a textbook, it might look kind of ambiguous. So I probably wouldn't write it like so. So of course we have 10, right, 1 sig fig, 10.2 sig figs. But then I'd probably say, go ahead and rewrite it, right, as 1 times 10 to the 1. Seems a little silly, but at least you can clearly see, okay, I have 2 sig figs. Versus this, where you're like, I'm not sure if we're ending a sentence or if they're trying to show me it's significant. And so, you know, you probably won't see this too often, but just in case, just be aware of that. All right, so let's do some practice now that we know how to identify how many sig figs. And so this is everyone's favorite topic because it just continues on and haunts us forever, the rest of the quarter. So again, right, keep this in mind when you're doing your lab calculations. I think one instance, well, I'll talk about it later. We'll talk about some examples. All right, so let's just go through the rules formally, and then we'll see it. And so it's pretty straightforward. So for multiplication and division, the least precise value determines our sig figs. And so again, we'll practice that. And then for addition and subtraction, it's the value with the smallest decimal measurement, so right how far out it's reported. But again, we'll practice this and kind of see how it works. And so if we look at our examples here, and I'm going to pull up my calculator just for clarity's sake. And so again, we're kind of thinking about what could happen in lab. And if you accidentally, right, didn't write, so this is again showing us why it's important to write 4.00. Like if you were again in lab, you'd want to accurately measure that. Because otherwise, you're left with this, which is 3.56 times 4. Now how many sig figs does 4 have? 1. So yeah, this is our limiting factor. So we have, of course, 3 from over here. And so again, just kind of plugging it in. So we see, so 3.56 times 4. So calculator spits out this answer, but now we have a problem. So we can only report this to 1 sig fig, so we have to round to 1 sig fig, which is why they reported it as 10. And so what I would kind of get from this is, again, right, this is showing you why it's so important to, when you're in lab, you get all your digits, right, you write everything down, so you don't get kind of silly answers like this where you're like, well, that's a little inaccurate, but, you know, it's probably not so inaccurate, we just didn't record everything properly. And then just watch those units, so centimeter times centimeter gives us centimeter squared. So again, similar situation. So which ones are limiting sig fig on this next example? Which one?
Which one does?
Yeah, which ones are limiting sig fig? So which one has the least amount? So how many sig figs is that?
2.
So 2. So again, right, same or similar scenario. So let's just work through it, punching through. So again, calculator spits out 10.25. So now we have to round to 2 sig figs. And so that's why we get our 10. And of course, this is one of those scenarios, right, where we want to show this is significant, so we could put a decimal, or it might be better, right, to rewrite it in scientific notation so we're not ambiguous there. So same thing, division works pretty similarly. So we have, again, only 1 sig fig here. So once we do the math, we can only report it to 1 sig fig. And then what do you notice about this last example? How many sig figs do we have? What are we limited by? So what number should we look at for the last one? We could also say, what are these, right? What do these look like to y'all? Yeah, conversion factors, right? So this is just conversion factor, conversion factor, conversion factor. And so it's only dependent upon what we started with, right? So we're saying, well, I want to convert 4.5 feet to meters. Doesn't matter how we got there, right? So again, it's just showing our conversion factors. We said they all had infinite sig figs. So that means we're limited by, again, what we were given. So that's 2 sig figs. And so then we can do all the punching in the calculator. Again, just for formality's sake, so we're all on the same page here. And so calculator spits out that. And then again, right, we have to round it appropriately to 2 sig figs. Questions on the multiplication, division stuff? And so that's why I was saying, again, just thinking of an example that we saw this morning. For your measurements and mixtures, right? I forgot what measurements people were getting, but 37.123, essentially 5 sig figs over 5 sig figs, right? And so when you do your percentage then, so obviously I'm just making up some numbers real fast, but my point is when you're doing your lab calculations, right, you want to give yourself all 5 sig figs then. So we have 5, 5, So then our answer would be 63.761%. So right, don't just chop off stuff arbitrarily, right? You have all 5 digits, so you can report it to 5 digits. And then, of course, pay attention, right, to all the density calculations. And so let's look at addition and subtraction, because, again, the density calculations, taking that volume difference, is where you can get into a little bit of sig fig trouble. And so if we go back to what it said we're limited by the smallest after, or sorry, the least accurate after the decimal. And so in this example, and I always say, you know, you can set this up like elementary school style or whatever, just to maybe make it obvious to help you see. And so we have 23.467 plus 313.21. So of course, this one is our limiting, right? Because it only goes 2 after the decimal point for addition and subtraction. And so then we would plug it into our calculator, formally get this, of course, 336.677. But again, we can only report to 2 after, so that's how they rounded to 0.68 there. So again, just watch that on your volume. Don't just drop digits either, right? If it's 6.0, leave it in there. And then this is what I call one of those awkward scenarios. So again, right, you want to give yourself the zeros if you have them, because this is saying, right, we couldn't measure it any more accurately than this. So we have no numbers after the decimal point. And so that's a little awkward, right? We do our subtraction, we get 456.32, but then we're forced to round up to the ones place. Yeah.
Why the 457 doesn't have a decimal point?
Yeah, I mean, we don't know why, right? So that's why I'm saying, like, somebody probably messed up in lab, right? Like, that's kind of the best explanation. Like, unless your ruler really is that inaccurate, but again, you were just kind of in lab, you know that you can measure more accurately than this. So, yeah, I would assume someone just kind of messed up, didn't give enough digits, and then you see that reflected.
Or could it be possible that the person didn't want it to be 4 significant figures?
I mean, you really don't want to do that, though, because, right, you always want to report what you have in lab, because if you just start taking away, you know, significant figures randomly from your equipment, then it loses its physical meaning and its relationship. So that's why I'm always saying, like, you know, get it right in lab, and then, of course, right, your calculations will just follow. So that being said, for, like, you know, grading purposes for lab, I'm pretty lenient anyways, but I'm just going to, like, follow, you know, your work. So if you leave off, you know, a bunch of numbers like that, you know, I'm going to just kind of grade it as such with that many sig figs, and I might make a note of, like, you know, next time it needs to be more accurate, that sort of thing. Because that's what we want to get at, right, is like, if you were doing this in the real world for, you know, real data points, you'd want it as accurate as possible. And then you want your data to reflect that. And then, yeah, we won't get into, like, error propagation, because that's also tied to this, but beyond the course. But that's also why it's important to give everything accurately to what your glassware or equipment is showing. And so then just kind of looking at this, I didn't want to belabor scientific notation too much, but here are just some right examples. Obviously, positive exponents means big numbers, and then negative exponents means small numbers. And then, of course, if you want more help with this, then, of course, like, I'm happy to meet individually, unless you have like a burning question right now about it. All right, so let's see what else we have. Oh, actually, before we move on, I did want to bring up a few of the homework problems. So blah, 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 rulers. So these are good, these calculation practices, but I wanted to bring up this 12.3 grams divided by 5, because this is a kind of a different scenario. Because if we just look at this, right, we're just looking at it, and if you just kind of follow along with the numbers blindly, like it kind of wants you to in a way, you would obviously just think that it has one sig fig, right? However, there's kind of an exception to this. So let's think about the different scenarios. So like, let's say we were in lab and we were measuring like a rock, right? Like 5 rocks. So basically we're saying we have 5 things in our hand that we can discretely count, right? We know there's 5 things. It's not like a population average, and I'll give an example of a population average. But basically, okay, we had 5 pebbles, maybe we got our average mass here of 12.3, and then we're going to divide it by 5, because again, we had 5 discrete pebbles. And so in that case, right, the 5 would not count as a sig fig, right? So it would just be infinite value. So in this case, it would be better to report to 3 sig figs. That just wasn't quite clear from this problem. So I'm not like marking anybody off or anything. I'm just pointing out what it's trying to get at. And then versus like a population average. So like the difference would be like, let's say you were trying to count, I don't know, how many birds are in an area, right? And then that's tricky. That would have a sig fig, right? Because you can't just capture the birds, right? And say, okay, I know I have 5 birds at this point. It's going to be, well, you know, at this time, you know, I think I roughly saw 5 birds in this area. So that's where the sig figs would count for the 5. But again, if you have things that you can hold in your hand and you can discretely, you know, count the population, then include it in sig figs. Does that make sense? And then for this one, I probably won't go over it just yet. And you can always look at the key if you have issues. But watch those units, right? So you have different units. So you'll have to do a unit conversion. But then keep your sig figs in mind as well, because it's easy to kind of accidentally add extra sig figs. And then again, just watch those units. Like we have a grams over grams, so that's going to cancel. And then grams per milliliter, right? That's just a density relationship. And then again, all these, right, are dictated. So 3 sig figs, 3 sig figs. All right. So the last bit on here is we want to look at our temperature scales. And so let's look at Kelvin, because that's probably the one you're least familiar with. So what's the Kelvin scale based off of? Like what dictates the Kelvin scale? Like why the numbers are the way they are?
I think that dictated by the absolute 0.
Yeah, so what's absolute 0 then?
It's the freezing point.
So it's not a freezing point. But what is absolute 0?
It's the lowest temperature you can easily get to.
So lowest temperature, but it's a theoretical concept, right? So it's our theoretical temperature, and it is the lowest, but what defines absolute 0?
no energy at all.
Yeah, no energy or no molecular motion is usually how it's phrased. So excellent. So no, I'll put no molecular motion. And so again, right, we had mentioned on Monday, so we said, okay, well, solids, right, even though they look solid, they're still moving, there's still electrons vibrating, right? They're wagging, they're stretching, they're doing all sorts of things. But at absolute zero, all of that would stop, so there would be absolutely no molecular motion. I was trying to find some good articles on that just because it's pretty interesting how they get down there. Oh, man. Basically, they have to like try to thermally isolate the system, which is pretty difficult. And then some other articles I was reading, I'll have to find better ones. But they were basically like shooting lasers at the molecule to stop the vibrational movements, and like that's how they were getting it close to the absolute zero. And I think they've only gotten to like 0.4 Kelvin is the coldest, at least from, if memory serves me. So good, so that's our Kelvin scale. So it starts at 0, and then now we can at least compare it to things that we understand. And so Kelvin and Celsius track pretty similarly in the sense that 1 degree increase in Celsius is also equal to 1 degree increase in Kelvin. And so you can see that clearly in the water freezes, right? So of course Celsius is maybe easier to learn since water freezes at 0 and water boils at 100. So nice, easy numbers to remember. And so with Kelvin, water freezes at 273. And then notice the 100 Kelvin difference to water boiling. And then, of course, if we compare that to Fahrenheit, well, that's kind of a mess, right? So Fahrenheit, water freezes at 32. And then this is what's awkward is you have a 180-degree difference between freezing and boiling, right? So it obviously doesn't track linearly. And then 212 is obviously the boiling point. And so I won't make you memorize any formulas. So even for temperature conversions, like I know they're open notes, your exams, but I'll still probably provide you these formulas. So you just want to take note of how to plug them in, right? So of course, if we're trying to go from Celsius to Fahrenheit, we would use this formula. And then you might see other forms of it. And all I mean by that is 9/5 is 1.8. So right, you might see 1.8 times Celsius plus 32. And then if you're going the other way, again, just order of operations, parentheses first. So do your subtraction and then multiply it by 5/9. And usually you see 5/9, not the 0.55. I usually see 1.8 more over the 0.55, but just be cognizant of that. And then conversion. So you might want to write this down. So our temperature Kelvin is equal to our temperature Celsius plus 273. And then I believe, because there's a more precise conversion of 273.15. So for the record, I really don't care about this 0.15. I really won't test on that explicitly like that. I was going to say the only point where it kind of comes up in the homework is like in number 2 on our temperature conversion. It makes this weird point of saying exactly into Kelvin. And so they were trying to say, oh yeah, add the 0.15, but again, like on an exam, I'm not looking for that 0.15. I really don't care that much. But if you check the key, right, you'll see that's why you get a little discrepancy, and sometimes it puts the 0.15, sometimes it doesn't. Again, it's really not that relevant. We usually don't measure temperature that accurately for our purposes anyways, so using the 273 is just fine with me. And so last little bit of lecture, again, I want to respect our time even though we're not doing a real quiz today, still trying to keep it to an hour. So density is our intrinsic property. So meaning it does not depend on the amount. And so that is useful, and why we care about that is we can identify substances. And so again, maybe you practice this in lab today, and it's just a ratio of mass over volume. So again, commonly we see grams per milliliter because we're working on our scale with grams. But of course, right, we could think of any other, like pounds per gallon, it could also be grams per liter, etc. It's just a ratio. So we have density equals mass over volume. And so we'll do this little example. But I just want to show you, have you all seen the triangle trick before? So the triangle trick is useful because you can just cover up whatever you're looking for, and then it tells you kind of what to do. So if you needed to find mass, you cover mass, and it tells you its density times volume. And of course, dimensional analysis can help too, but good to have several tricks. All right, so let's do this one. We'll do these problems. So first do this one. 73.2 milliliters, mass of 61.5. What's our density? And so what do we get for our answer for this first one? .84, and then grams per milliliter. So I like it. My one tiny criticism of your answer is just give it the 3 sig figs, right? So 0.840 grams per milliliter. So we have 3 sig figs in our problem. Again, multiplication, division, just limited by our least. Again, they're both 3, so 3 sig figs there. All right, try this last one. And again, this is where triangle trick may help you if you're still struggling a little with dimensional analysis, or you just want extra sanity check. And then this one, again, triangle trick, we're trying to find volume. We could cover it, so it tells us we should take our mass divided by our density. And then if we do our dimensional analysis, that would also make sense. So divided by density, so look at those units, so then you get grams on bottom, centimeter cubed on top, which is going to give you a volume. And so what do we get for this one? A, B, C, D, E. D. Do we have other votes for D? Some thumbs up. Excellent. So D is the correct answer if memory serves me correctly. I'll punch it in just for, whoops, it would help if I punched it in properly. So yes, D, I was just off on my punching. Let's see. Other last bits of the chapter. This is just a definition. It comes up, and so we should just mention it. So your book says that specific gravity, so really specific gravity is just a ratio or comparison of any densities. Your book makes it more specifically of a comparison of a density of a substance to water. And then that's also kind of silly, in my opinion, because what's the density of water? Water special. No guesses? Water's like the standard for everything. So it's 1, remember. So water has a density of 1 gram per milliliter. That's also why it's special. There's a lot of reasons why it's special and wonderful. And so then this, again, in my opinion, gets kind of silly, but we should go for our definition. And so now let's just look at an example of what it's trying to say. And so the density of hexane, for example, is 0.659 grams per milliliter. And so then if we were to ask for the specific gravity of hexane, again, by your book definition, it's compared to water. So then it just becomes 0.659, right? And your units cancel out since it's just a ratio. So again, I kind of think it's silly, but it's a book definition. It's in there, so that's what specific gravity is just a comparison of densities. All right, I think that wraps up chapter 1. And so, like I said, we'll practice our format of how the subsequent weeks will go. So, of course, like I said, I'm just handing out a welcome quiz today. So no studying required. Next week, we'll take our quiz over chapter 1. And then, so kind of the idea is, you know, you can take a break if you need. I'll just go ahead and hand out the quizzes, though, because some people like to get out of here. I encourage you, though, to stay. I know many of you, right, finished your lab in lab, so that's a good idea. I would stay and ask questions during this time if you're having issues with other things, right? Recitation is kind of your period, right? So if you need to just sit here and work on homework after your quiz, you know, that's fine, that's great, that's what I'm here for. Take advantage of that. If you want to run away, you know, that's also cool. You can do what you need to do. Yeah, just get the quiz back to me before you start running away. And otherwise, I'm happy to field questions. Yeah, you can turn in the lab now if you're done. Otherwise, ideally by next Wednesday, plus or minus a few days if you need. Thank you. Thank you.
I just had questions with this section. So what are we required to do exactly?
Just what you're doing. The only thing is you want to be like consistent with the sig figs, because like on this one, you know, my only criticism would be that it looks like you have 3 sig figs there, but we only have 1 originally, so you just want to write 5 times 10 to the 2.
Okay, I do understand. And this one?
So then
Also the
this
same
one you
thing.
want to do the calculation. So yeah, you're right that it's 3 sig figs, but then yeah, give me the number.
So you want the answer and the significant
Well-
figures of the answer?
You don't have to write how many sig figs, but just report it to the correct number, yeah.
Or the answer, I need to work it out.
Yeah,
Okay. And this one, is it a multiplication or what?
yeah, multiplication,
Subtraction.
yeah.
And then this one?
So those, right, that's what I was saying, you only have 3 sig figs there,
So my
so.
answer needs to be 202.
Well,
I mean, sorry, 1, yeah.
but then round it, so .203, right, because you have
Oh.
the 8 there, yeah,
Yeah.
so it should round up. But
Okay.
then, yeah, that one you can just chop off to 36.2. Yeah, 3 sig figs there, so you'll have to round up to 3.46. But yeah, just be consistent.
Okay. And then when are you going to make this?
I think it's technically due on Monday,
Okay.
but again, right, if you need another day or two.
And lastly, with this one, was I supposed to literally measure this with my own ruler?
No, you're supposed to take like this ruler, so this would be 5 point something. And same thing with this one, right, 5.4 something.
Oh, okay.
And then, yeah, that
So
one.
I got lost. And I think that's it. Okay. So for recitation, that's where we ask questions if we have one.
Yeah, yep.
All right then. Yeah, that's it. Thank you.
So yeah, you're free to go. You're good.
Good luck.
Oh, thank you, thank you. Thank you. Thank you. Have a good weekend. Thank you. And yeah, did you put the quiz in that file? Perfect. Y'all were fast with the labs. It's good to
would it be just 4.0? I think it's around about 7. So would it be just 4.07? Would it be 4.007?
Yeah,
So
007.
Okay.
Yeah, because it's not past the 4.01. Yeah,
Okay.
exactly. question?
So for this will be 3 sig fixed, but for the bottom one, it will be 2, right? Because
So
these
the,
zeros won't count.
no, they would count because, yeah, because they're
Okay.
showing how
So it will be
accurate,
4?
but you're
But it will
right.
be- So I would go with 3.
Yeah,
and that's
exactly.
it. Okay.